Hi everyone, welcome back to the channel. Today we're talking about logistic regression. So specifically what I'm going to be looking at is prediction of rice types or two classes of rice based on numeric values of some other selected continuous variables. So before I jump into this, I wanted to mention that the data set that I'm using is this rice data set donated on 10/5/2019, and this includes some information about rice as well as some images, and specifically we'll be using the numeric data. But you can find this at the UC Irvine Machine Learning Repository, which is a great place to find information that you can use for machine learning projects. So with that said, the first part of this is really just setting up some libraries, and then importantly there is a line here for set seed. I just picked 1, 2, 3, 4, 5, and this is important for reproducibility. So every time I run this script, it performs the same way. So whenever you're doing something like this that involves any kind of randomness or variability, it's important to get that set up so your results are the same each time you run it. Now, for loading the data, I'm reading in an Excel file, and I'm making sure that the class variable is set as a factor. So that's going to include two different types for the rice types, and so I'm going to force that to be a factor. And for my own sake, I just like to have all the names for the variables in lowercase and as simple as easy as possible. So I'm really just manipulating that because I like the way that that looks. And then I'm looking at the data set here with the little preview by just calling the name of the data set. So here we have a tibble, which is again a type of data frame, and we can see that it includes the variables area, perimeter, major axis length, minor axis length, eccentricity, and convex area, as well as extent, which is not seen here, and then class, which is the factor that we set up. And the class includes the names, so we'll see that in a moment. But here it's important to know that we have a few different numeric variables we can choose from. These are all doubles, which is indicated here in the tibble format. And there are a little over 3,800 rows of data. So before we get into logistic regression, just as a quick idea, logistic regression is a method that we can use to classify individuals. So using the numeric data, we can put those individuals into different classes. In this case, we have the class labels, and so what we're going to do is try and learn those labels and their association with the numeric values, and then later use that model that we create to predict the association of new individuals. But before we do that, there are some assumptions with logistic regression that you have to pay attention to. One of them is that you have a binary dependent variable. That's the class. So in this case, that's what we have. The observations are independent. We'll just have to assume that that's true here. Low or no multicollinearity. We'll talk about that in a moment, but that's essentially when you have variables that predict each other. So if you have A and B and C predicting the variable D, then if you have a multicollinearity situation between B and C, that means they're highly correlated. Like B can predict C in some way or vice versa. And so you don't really need both of them in the model, and by including both of them it creates problems. So you might choose a model that has A and B or A and C, but you don't need A, B, and C together. So we'll look at that. There's also one that's a little bit weirder here. It's a little more complex, but it suggests that there's a linear relationship between the input variables, which are all of our numeric variables, and the log odds of the output variable. So we'd have to look at the likelihood of each of those classes and then do a little transformation and then look at the results of that versus each of our input variables that we choose. And then the last one is large sample size, which in this case is okay. We have close to 4,000 individuals, so it's fine. So we're going to look first at our data and just see what's going on. So here I'm just checking the levels of the class variable, and we find out that there are two, and their names are Cameo and Osmanchik. So that's the two types of rice. And then as far as our general approach for building the model, what we want to do conceptually here is split the data set into one large part that we can use for training our model and one small part that we can use for testing our model. And it's important that we do that because that gives us a good amount of information that we can use to train the model. So we can build it with more confidence that we have a lot of information in there that goes into helping it to learn what the classes are based on the inputs. And then we also have a substantial amount of data that we reserve that we don't look at for training. And so that's an important thing, so we can test our model against something. So here we'll do the split, and in this case we're using this create data partition function, and the amount of information that you put into the training is 80% in this case. So this is p equals 0.8. That's the proportion of that data set that we're putting into our training set. So functionally what happens here is we're adding a label, and we're just calling it split, and then we're going to use all of the individuals that got that label split, and we'll put them into data train, and everybody else that didn't get that goes into test. So we're getting an 80-20 split of our main data set here. And then we can use the table function here and a few little tricks to end up getting a number of individuals in each of those splits and then the proportion in each of those splits. So what we end up with is the looking specifically at the cameo types. There are 1,304 of them in the training data, and then we are seeing that there's about 43% of those individuals in the training data are of the cameo type. So the next thing I want to look at is multicollinearity, and again, this is a bad thing, so you want to avoid that, and so it's important to check and just make sure it's not a problem. And if you have individuals, or if you have variables that are involved, you can sort of figure out what to do with them. One way is to just get rid of one of those problematic variables. And in our model, I'm not going to be using very many of the variables in the data set. So we'll have a very small model, but again, it's good to check. So the first thing that you can see here, I have a model, and I call it model VIF because we're specifically looking at this variance inflation factor as a way to check multicollinearity. The variance inflation factor, or VIF, is explained elsewhere online, but it's essentially a measure of the degree to which the predictor variable is explained by other predictor variables. So we can look and see each of the predictors in our model and see if they're explained by somebody else. Now, in here, I'm creating a general linear model, GLM, and the model is class, and then there's this little squiggle, tilde, and then area and eccentricity. So that is the model, and what it means is that I'm looking at area and eccentricity being used together to predict class. So the data are coming from our training data set, and in this case I'm specifying a binomial model, which is the one we want to use because we have two types of classes. So we're going to be looking at this, and then we'll use this VIF function to check out the two inputs in that model. And we can see that the values here are about 1.22 for each one of them. And if we go up to this little interpretation list I've put together, a value of 1 is what you want. It suggests no multicollinearity. A value of 1 through 5 is moderate but tolerable, and then anything over 5 is generally pretty bad, and it requires further investigation. So here we have 1.22, which is on the low end of this middle category. So I'm not really worried about it. The other assumption that I talked about is a little more complex, and I'm not going to dive into a huge background on this, but essentially what we can do is look at the relationship here between the input variables and the logit of the output variable. Now, our output variable is right now 2 classes, a factor. And so there's a little bit of a transformation in here to get the probabilities of belonging to those classes. So that happens first to make some numeric values. And then the transformation to the logit takes place down here, and using the mutate function that's appended to the existing data set. And then what we're going to do is just look at the value of each one of those and then the logit. So for that input variable area, there might be a value here, and then the logit value is negative 9.10. So in our case, again, the model itself is area and eccentricity predicting class. So those are the 2 values that are included in this predictor list. And then if we scroll down here and look at the plot, I'm using ggplot just really quickly to do this, we can see the results of this. And what you're looking for here is a linear relationship. Now, we can tell that these are not perfectly linear. There's some curvature here, especially on the ends of these. But for the purposes of this explanation, I'm going to assume that these are essentially linear. I'm looking mainly at this large blob in the middle of each one of them, and I'm not really super worried about it being super highly unusual and curved. And we can dive into that later. There are some other methods you can do to correct for that. You may want to look at the Box-Tidwell transformation to correct for any excessive curvature in these, but we're going to assume that these are linear for our cases. So the model itself is constructed here. We'll look at that in a minute. And we're also going to be looking at something called the confusion matrix to check the performance of our model. So here, a confusion matrix is essentially a table that tells you about the predicted value and the actual value. And so what you want to see in your model is that the predicted value matches the actual value. So that suggests that things are working well. If you have a huge problem in your model, you won't get really good matches between predicted and actual values. So in our case, we have our model, which I'm calling model. We're going to use this train function. And again, we have the same model as before. We have area and eccentricity predicting class. And we'll use our training data. And in this case, again, it's a general linear model and a binomial type. And then to get it all set up, we're using this predict function with our model and our test data. That was the data set that we held out, the other part of the split. And then the confusion matrix can be constructed using this confusion matrix function, using the prediction in the line above, and then the class variable from our test data set. And then we can just print the results out. Now, I believe this is from the caret library, C-A-R-E-T, and it does a really nice job because it gives you not only the confusion matrix, but all the stats around it. So here we can see our prediction is Cameo, and then the actual value is on the top. And we can see that there are 291 in that box. So the upper left quadrant here, the predicted and actual values that match, there's 291 of those. For the other class, this other rice type, Osmanthus, there's a value of 406. And then the bad ones where we predicted Cameo, but it was actually Osmanthus, there are 30. And where we predicted Osmanthus, but it was actually Cameo, there are 35. So relatively few in those bins, which is good. So overall, we have an accuracy of about 91%. And I'm not going into all of these terms. It's important to understand all of the terms here: accuracy, sensitivity, specificity. I'm not going to get into that in this video. But generally speaking, the accuracy is the ability of your model to predict the classes correctly. So we can see that we have a really high value of about 91% here. And then looking at the other values, they're also pretty high. So that's good. That's an indication that our model is working well.